Okay, guys, so this is lecture 1, unit 4, and this lecture is on forces at angles. There are going to be 4 lectures in this section. This is just the introduction one. Okay, so let's get started. So by the end of today, you should be able to describe angled forces in terms of x and y components, and use trig to resolve those forces into their components. You should be able to solve for the normal force when an angled force is applied, and calculate the net acceleration of an object with angled force. Okay, so the main piece about this section that you need to be aware of, I'm just going to make a note up here, is that the normal force is no longer equal to the opposite of gravity on these angled forces. Okay, so up until this point, so on the previous unit, that was always true, right? They always balanced. But because things are angled now, it's not necessarily true. All right. Okay, a couple things to remember. All right, I'm going to try to get this thing to stop doing that annoying in and out thing. Whoops, that's not what I meant to do. Okay. All right, so given the following vector, find the x and y sides of the triangle. Okay. And basically, remember, this is like how we resolve these into, if this was a force, this would be fx and this would be fy. Okay, and for this one, instead it would go left and up would be fy. Just keep in mind that the arrows have to match, so if this is going up and to the right, then you should be to the right and up, and this is going left and up, so it should be left and up. So make sure you're not drawing arrows into the opposite directions. Okay. This is all review, but example 1, break the force vector on the right into x and y components. So fx would be here, fy would be here, right? The 25 is really on this side. Right. So hopefully you remember that if we use SOHCAHTOA, this is the adjacent side, this is the opposite side, this is the hypotenuse. So if I want the adjacent, I'm going to go ahead and use cosine. So cosine of 55 equals adjacent over hypotenuse. And then if I want to solve for it, it's 25 cos 55. Right, so hopefully that's coming back. And that gives us 14.3. Since this is in newtons, these sides will be in newtons. Okay. For fy, we're going to use sine, so it'll be 25 sine 55. Okay, and if we do that, we get 20.5. Okay, so hopefully that's a review, but we're basically just essentially breaking this force vector into its horizontal and vertical components. All right, that's all we're doing. All right, let's move on here. All right, in the last test, all forces were conveniently applied either horizontally or vertically. Now we will look at problems in which forces are applied at angles. We're going to, again, solve for net acceleration, weight, and frictional forces. Okay, so it's the same processes. That's why I said that if you didn't understand last unit, that this one would be harder, because you need the basics of last unit in order to do this unit. All right. So finding the normal force, and that's what usually is the hardest part about starting these angled force problems. All right. So if an object is pulled or pushed along a flat surface, then the net vertical acceleration is 0. Right? We can agree that if it's being pulled in the x and y, or in the x direction, that the y net force is 0. Okay, meaning that the up force is equal to the down forces. So basically, the F up equal F down. Right? Because our forces are now angled, we will get an additional force in the y direction. We'll call it Fy. Okay? Since the force of gravity cannot change, this means the normal force changes. Okay? So sometimes it'll be less than gravity, sometimes it'll be more than gravity, depending on the situation. So here's an example. So a 15 kilograms, so there's the mass, okay, is pulled at 45 degrees. So they're pulling here, and this angle is 45 degrees. with a force of 55 newtons. So I'm just going to go ahead and label that there. Okay. Draw a free body diagram that shows Fg, Fn, Fy, and Fx. So let's first break this up. This is going to have an Fx and it's going to have an Fy. Okay. And essentially it's pulling here, right? But we're not going to put any angled forces on the free body diagrams. So we have gravity down. We have normal up. Okay. We also have Fy that is up. Okay. Then we have Fx, which is pulling to the right. And they're not showing any friction, so we'll just leave it just like that. Okay. Make a net force equation for the vertical forces. Okay, so F net in the vertical would be F up minus F down. Right? So we remember that. Okay. So this is our F net equation, and we're going to solve for the normal force. F net is going to be 0 because this thing is being pulled in the x direction. So in the y direction, this is going to add up to 0. So in that case, I can add Fg to the other side. Actually, let's add Fg and subtract the Fy. Right? Okay. And Fg is mass times gravity, so this is going to be 15 times 9.8. Fy is going to be 55 sine 45. And that's going to be equal to Fn. So this is 147. And this is 38.9. So essentially what's happening is that this person, when they're pulling it, they're sort of lifting up a little bit, but it's not coming up, but they're pulling up a little bit. And so they're essentially taking some of the weight off the ground and therefore making it so that the ground doesn't have to push up as much. And so the normal force is actually going to be less than it normally would because the Fy is helping pull up against the gravity. So these two are essentially working together to fight gravity, right? So if we do the math, then we get 108 for the normal force, which is less than the force of gravity because this force is helping pull up a little bit. Okay, so hopefully that makes sense. Let's move on to the next page. All right, here we are. Okay. So this one, that last one was a pull. This one is a push. Okay, and they're going to be different. So example 3, this guy is pushing a lawnmower. Okay, and because he's pushing it, he's sort of pushing down and to the right at the same time. Right, and so we get a vector that looks like this. Okay, so it says it's 25 kilograms, so let's write that down. And it's pushed with a force of 85 newtons at an angle of 65 degrees. Okay, I'm going to go ahead and assume that this is the 65 degrees. It should be more clear where the 65 degrees angle is, but for now, I'm just going to assume that it's there, okay? It's fine for the example. In your test, it would be more clear. All right, so draw a free body diagram that shows Fg, Fn, Fy, Fx. Okay, so here we are. We've got Fg down, right? We've got Fn up, Fx to the right. And if you look at our picture now, the Fy is downward, so it would be added to the gravity. Okay, so now two things are pushing down. All right, the net force equation, up minus down. And Fy is also down. So you can do that. You can do two minuses like that, or you can parenthesize them and add them together. Either way, it's the same thing if you distribute the negative. Whoops, sorry about that. Okay, so you can either do two negatives, or you can put the negative out here and add them, and then just distribute the negative, which is the same thing. Now, if we're solving for the normal force, then we're going to go ahead and add both of these two to the other side. Oops, sorry. So the net force is 0. Okay, so we'll add those to the other side. Fg is going to be 25 times 9.8. While Fy is going to be, actually now this is the adjacent angle. It's going to be 85 cosine, or sorry, yeah, 85 cosine 65. 65. Okay, so let's see, we get 25 times 9.8, which is 245. And then 85 cosine 65 is 35.9. And so the normal force is actually going to be much greater than gravity in this case, at 280.9, so 281, right? Which is bigger than gravity. Gravity is 245. And the reason it's bigger is because now this guy is pushing down into the ground, right? Which means the ground is going to have to push up against gravity and against this guy's push into the ground. So normal force actually has to counteract the gravity and the y. Okay, and that's why it's bigger than gravity. All right, the force of friction is affected by the normal force. That is true, right? We know our frictional force is mu times the normal force. So which situation, example 2 or 3, would increase the force of friction and why? Well, this should be pretty simple. Force of friction is directly proportional to the normal force. As the normal force goes up, friction goes up. So if you look at both examples, example 2, the normal force, sorry, I'm struggling here. The normal force was 108, right? Normal force was 108. It was less than the force of gravity. Whereas example 3, normal force was 281, more than gravity, right? Because of this push into the ground. So because normal force went up, friction will go up. So the friction is actually bigger in example 3 because higher Fn. Okay? So by pushing into the ground, you actually increase the friction. All right. I gave you guys a blank sheet of paper in your packet right after this page because this example is really long. And so I gave you a fresh sheet of paper. So what I'm going to ask you to do is just go ahead and get that fresh paper out. And we're going to just do, I'm going to fold this here. And we're going to go through that example, but I'm going to do it on a nice blank sheet of paper here. So we'll just go one step at a time. Okay, so we'll just do one step at a time. We'll start with A here. All right, but you won't be able to fit it on that page, which is why I gave you a separate sheet. All right, here we go. Hopefully this will stop doing that crazy focusing thing. Let me see if I can stop it. I don't know if I can, but we'll see. All right, a heavy box, mass 25, so let's label that. Okay. Is dragged along the floor by a kid at a 30-degree angle with the horizontal. Okay, so it's like this, right? And this angle is 30 degrees. We've got Fx and Fy. Okay. With a force of 80 newtons. All right. Which is the maximum force the kid can apply. Draw a free body diagram. Okay. So remember, we don't put angled forces on our free body diagrams. So break it up first and then draw it. So we have Fg, Fn, plus we have Fy going up. We have Fx. And I'm just going to guess that there's going to be some friction. Okay. So that's my free body diagram. All right. A is done. Okay, B. So here's A. Let's go to part B. What is the normal force? All right. Well, we know the box is being pulled in the x direction. So the y direction net force is 0. So I'm going to start by writing a net force equation in the y. Up forces minus down forces. Okay. I know this is 0. So that means if I want to solve for normal force, it's going to be equal to Fg minus Fy. And then I'm just going to go ahead and plug in the numbers that I know. So 25 times 9.8 minus Fy is going to be 80 sine 30. Okay, so 25 is 245. This is 40. So Fn equals 205 newtons. Okay, makes sense. I double check. Makes sense that it would be less than gravity because this Fy is helping. Okay. All right. Part C. What does the normal force decrease or increase if the angle of pull increases? So if this angle increases, meaning that this arrow goes higher and higher, meaning Fy gets bigger and bigger, then the normal force should actually decrease, right? Because the more the Fy is helping, the less the normal force has to do, right? So normal force increases if theta increases. Oh, sorry, decreases. Just said that. Normal force decreases. Okay. Part D. Assuming no friction, what is the acceleration of the box? Okay, so let's assume that friction is 0 here. Okay, so then the net force in the x direction would just be the positive minus friction, which would be 0. Okay. All right. And let's see, so then the net force would be ma. Fx is going to be 80 cosine 30, which is 69.3. Okay, divide by 25. So I get A equals 2.77. Okay. E. Assuming it begins at rest, what is the speed after 10 seconds? So using what I know from my previous answer, writing down the variables, I'm looking for VF. I'm going to use this equation. So VF would actually be 27.7 meters per second. Okay. All right, F. Let's see, let's do F over here. I'm going to go ahead and tuck this part under. And that's not going to help me. Let's just fold it over a little bit. Okay, for F. Okay, is it possible for the kid to lift the box by pulling straight up on the rope? Well, the maximum force the kid can apply is 80 newtons, and gravity is 245. So I'm going to say no, right? Because even if the kid pulled up with 80 newtons, gravity is 245. So there's no way that he can lift it. Okay. All right, G. In the absence of friction, what is the net force in the x direction if the kid pulls at a 30-degree angle? Well, we already did this, right? We already said the F net, if there's no friction, is just equal to Fx. And Fx is equal to 80 cosine 30, which we already got 69.3 newtons. So we already did that part. Okay, that part was done up here. All right, and then H. In the absence of friction, what is the net force in the action if the kid pulls with 45 degrees? So exact same net force equation, right? Except that now it's 80 cosine 45, which would give us 56.6. And then I says, in the absence of friction, what is the net force if the kid pulls with 60? So this is a little repetitive here. But I think what they're doing is getting to the idea that what happens to, let me get 40. Okay, so then J, the kid pulls, let's see, the kid pulls the box at a constant velocity at an angle of 30 degrees. What is the coefficient? Okay, so if it's at a constant velocity, now we know there's friction. Okay. So just redraw the free body diagram. Okay. At an angle of 30, so now our net force equation equals Fx minus friction. Right. Constant velocity means that net force is 0. Fx is an angle of 30, so we know that this is 69.3 minus friction, which is mu times the normal force. Well, we found the normal force in part B, which was 205. So this is actually becomes, right? Subtract the 69.3. Just going to move the mu to the other side to make it look more normal. 69.3 divided by 205 is 0.34. Okay, so that's how we find mu. Now, part K, which is the last piece here, I'll do over here. Fold this a little more so you can see. Alright, part K. The kid pulls the box at an angle of 30, producing acceleration. Okay, so now A is 2. What is the coefficient of friction? Okay, so same idea, right? Here's our free body diagram. Net force is the same equation. Fx minus F friction, right? But now F net is not 0 because this was a constant velocity. This is actually has acceleration of A equals 2. So M was 25 times 2, so that's MA, equals, Fx doesn't change. She's still pulling with the same force, so this is still 69.3. This is mu times 205. Okay? 25 times 2 is 50. All right. I'm going to subtract 69.3. So that's negative 19.3 equals negative 205 times mu. Divide by 205. And now the coefficient equals 0.094. And the reason that the mu changed is because it basically said that if we don't change the pulling force, but the acceleration is different, then that must mean that the friction is different. Okay, and so the mu has to be different. Okay, so they just made us find both. All right, so that is the end of that problem, and hopefully that made some sense to you. Okay, all right, write down any questions you have, and we'll practice this stuff in class.